Hi class, Dr. Searcy here with the video lecture for the textbook for Chapter 5. As you can see, the title of Chapter 5 is Z-scores, location of scores and standardized distributions. In this chapter, we're going to start to move forward talking about some new things. So I thought I'd begin by doing a review of the information that you need to remember as we venture into this new area. The first thing I want to remind you of is what the mean is. Right, so let's remember the mean is basically the average that a researcher would calculate. The formula for it is basically where you take the sum of some collection of scores that you have and divide them by the number of scores in that collection. Remember that when we do this with a population, we refer to the mean with the symbol mu. However, if we are going to calculate the mean using sample data, then the symbology changes a little bit. Our symbol for me is X bar. Remember that if you're talking about the sample mean from the book refers to it with the uppercase M. But another difference between the population and the sample is that when you refer to the size or the number of people in the group, instead of using uppercase N, you're going to use lowercase n. But it's still the case where you're dividing the sum of the scores that you got by the number of people in your sample. So big piece of information moving forward is to remember what the equation is to calculate the mean, and also just to remember what symbols you use depending on whether you're talking about the population or the sample. Another thing that you want to remember moving forward is what the standard deviation is. So let's just remember what the mathematical formula is for it. Basically, if we're talking about a population, we are saying that we're going to be solving for this lowercase sigma. And the equation that we're going to go through is we will have found out what our sum of squares is for some collection of data that we have. And we're going to divide that sum of squares by the number of people in the group, and then you're going to find the square root of that figure. Remember that we're using the lowercase sigma if we're talking about the population. However, if we're talking about sample data, then the symbol that you're going to use is the lowercase s. Another thing that you want to remember is that when calculating standard deviation for the sample, the formula starts out being the same. You still have a sum of squares that you're going to be dividing, but now it's going to be divided by the degrees of freedom. Remember, the degrees of freedom simply is the number of people in your sample minus 1. But once you've figured out what the quotient is from that division problem, then again, you will find the square root of that, and that will be your sample standard deviation. Beyond that, some more information that you want to remember is how histograms and curves work. So first off, just to remind you, a histogram is a type of graph where you are showing data, right? And the way the graph works is on the x-axis, you have tick marks representing the different x values that you represents the range of the x values that you had in your sample. The y-axis is going to show the frequency or how often each x value occurred. And the way that you're going to represent that is with the height of each bar. From there, remember though, that one thing that we're doing with histogram is we're then taking the data and drawing a curve over the data, primarily to see if your curve is a smooth or a normal curve, or one of those other kinds of curves that we talked about, that positive skewed curve or that negative skewed curve. However, when you have data that falls under a smooth curve, then a way that we're talking about representing that data is by this type of graph. right? So we're imagining that we've got data underneath the curve. But the important thing that we're starting to talk about here now is how we label things under the x-axis. So to begin with, remember that you still have your x-axis with your tick marks for your different x values. But below that, we've started to talk about how you also can be thinking in terms of a row that would represent the range of the mean. With this, a big thing that you want to remember is that when we talk about the mean being under a curve, the mean is always that x value exactly in the middle of the curve. So I'm just going to put like an x bar there. And often, when you're presented with data, in the book, you will often be told what the mean is for that sample or for that population. So in this case, where we're saying that x bar equals 47, that number 47 could go right there, right? And that's saying the middle of the curve is the mean. We've been told what that mean is. It's 47, so the 47 on the number line is where the mean goes. Another thing that we've started to talk about too, though, is how you can plot the standard deviation right under that x bar, right? So standard deviation, this stuff that we're talking about up here. Remember, the standard deviation is basically a standardized distance away from the mean. And that way that we're representing it on these curves is we start counting away from the mean. And the way that we do that is by always noting that right under the mean, the standard deviation number is 0. And as we move away from the mean, then we can have tick marks that represent these standardized distances from the mean. For instance, I could put a tick mark here and a tick mark here. What would those tick marks be? That would be a 1 here and a 1 there. Why am I putting my two 1s there? Because we're saying that the standard deviation is 3, right? So we're saying that I'm moving away from the mean, the 47, 3 points away this way, so that would be 48, 49, 50, and I'm also doing it in the other direction as well, right? So we could say 47, 46, 45, 44. So what we're saying with that is, whereas the mean of this sample is 47, one standard deviation away from that is 50 on the x line, and then another standard deviation in the other direction is 44. Right? And we're saying that that's the distance because we've been told that a standard deviation consists of 3 units, so we're going 3 units out that way and 3 units out that way. Okay, so that's our review. And that's how you want to remember some stuff as we move forward. The thing that we're talking about that's new in this chapter is this idea of what a z-score is. So just to begin talking about z-scores, let's first note what the definition of a z-score is. We can define it as the number of standard deviations from the mean that a data point is. Okay, so I'm not sure if this means very much, but basically what we can say we can do is we can put yet another row of information under our histogram or our curve. And we can say that new row is the z row. One thing that you'll see is that the numbers on the z row track with the numbers on the s row or the standard deviation row, right? So when you're counting z's, we still say that the z has a 0 right under the mean. And also, the z is going to agree with the standard deviation units, right? So if we have a standard deviation unit of 1 right here, we'll say that we come a z there as well. One difference is that when you move away from the mean to the negative area, right, or below the mean, then we say that the one that would go here would be a negative one. So the one for z's, the one that's above the mean is a positive one. The one that is below the mean is a negative one. Okay, so let's think about, if we're now going to be talking about the z, how do we actually acquire a z score? The way that we do that is through another mathematical formula. And so I'm going to show you what that formula is. I've got the word formulas here because just like we had for our means and our standard deviations, there's a formula for the population z versus a formula for the sample z. So let's talk about the population formula first. That's this very easy to solve formula here. First thing that we need to point out is what are the different parts of this formula. Well, actually, the very first thing we ought to point out is that to acquire a z-score, we basically calculate a division problem. So what are the different parts of this division problem? First, we have an x here, and that's going to be some x that's going to be anywhere on your number line. We're just going to pick one and put it there. Next to that x is minus mu, or in this case, we're talking about the population formula, so minus a population mean. One thing that you might want to remember from previous lectures is that x minus mean is what we were referring to as the deviation score. But below that, in the denominator of this division problem, is always going to be the standard deviation, right? And just so that you can see, we often know these values. For instance, we're going to be given some x value. We're always going to be told what a mean is, so we're always going to be able to pop that in here. Or at least we're often going to be told what the mean is. And so we usually be able to pop that value in there. And same thing with the standard deviation. We'll often be told what the standard deviation is, so you'll be able to pop that information into this part of the equation. So now let's just take a look at what the sample version of this formula looks like. Again, you're solving for a z. You still have some x value that you're being given, and you're still going to subtract a mean from it. In this case, though, it's going to be the sample mean, and that's going to be above the sample standard deviation. Okay, so a couple of points that we need to make about what the z-score is doing for us. First point that we need to make is with regard to the sign of the z-score. By sign, I'm referring back to this idea that you could have a z-score that's positive or a z-score that's negative. And here I'm just going to tell you what that means when it's positive or negative. Basically, if the z-score that you obtain has a positive sign on it, that just simply means what I've already said, the x-score is above the mean. So you're going to have some x-score that's going to be in this range. On the other hand, if you have a z-score with a negative sign on it, that simply means that the x-score is going to be below the mean. It's going to be on this side of the average, or the mean. Another point that we want to make is the numerical value, right? So we're solving for z, therefore z is going to be some number that we're going to obtain. What does that number mean? Basically, it means that that number is the distance of the x-score from the mean. One thing that you may want to interpret from that is the smaller the z-score, the closer it is going to be to the mean. The larger the z-score, the further out, or the further away from the mean is going to be. Okay, so just to kind of begin thinking about this, I want to go ahead and run through a z-score problem with you guys. Just in a quick example here. In this example, you're being shown a curve. You're being told that this is a population data. How do we know it's population data? We know because we've got this sigma here representing population standard deviation. And it's saying that the population standard deviation is 3. We're also being told that we have a mean here, right? And I'll make sure that you remember the mean is this line here. I'm using a mu because we're talking about population data. And what we're being told is 70 is the mean in this distribution. Now, what we're being asked to do here is take this x value of 76 and figure out what is the z-score for that 76. How do we go about doing that? Well, we set up our z equation. Notice I'm writing my z's with this line through it, and that's just to make sure that you see that it's a z, like not a number 2. But according to the equation that we have here, up here, I'm going to put a value here, here, and here. First value I write in is that x value. We've already been told that x value is this 76, so I'll put the 76 there. We know that it's going to be a subtraction problem, so I'll go ahead and put my minus sign in. We know that we have to write a mean value next to that minus sign, and so our mean value that we're going to write in is that 70. And that's all going to go above our standard deviation, which we've been told is 3. So now at this point, I'm going to go ahead and solve the equation. First thing I'll do in solving is take care of that subtraction problem in the numerator, and that gives us 6 divided by 3. But to finish that problem off then, we see that z equals 2. Right, 6 divided by 3 is 2. Okay, so now what you want to see is how that 2 is meaningful to us. Let's go ahead and go back to drawing our lines underneath the curve. Right, so say we have that mean line, that's that 70 there. If we have our standard deviation line, again, we're saying that 0 goes right under the mean. If I'm going to draw my 1 for my 1 standard deviation unit, I know that I'm going to draw it 3 ticks away from the mean. So it's going to go right there. And then if I wanted to draw another standard deviation unit away from that 1, I'd put my 2 right there. Right, so we're moving away from the mean 3 tick marks at a time. So first standard deviation is 73, second standard deviation is 76. And the thing that you want to see here is that when we go in to put that z row, the z row matches the standard deviation line. We still have our z of 0, our z of 1 right there, and then we have this z of 2 right here. Right, and so it's important that you're seeing that the z and the s rows match up, but what's really important is to see how z and s are different from each other. S, or standard deviation, is just telling you this standard distance that any number could be away from the mean, right? So a 73 is 1 standard deviation unit away. A 76 is 2 standard deviation units away. Z, on the other hand, what its purpose is to pick any number on the number line and tell you where that number is in terms of standard deviation units, but we call it Z units. Okay, and in this case, that number 76 is 2 standard deviation units away from the mean, and that's why we have it lined up like this. Okay, so let's go ahead and keep on going. Now I want to talk about some practice problems with this. First practice problem that we could have is this problem here. Right, and I just want to read it to you just to make sure that we see what the important information is in the practice problem. It says that in a population with a mean of 65, a score of 59 corresponds to a z of -2. What is the standard deviation for the problem? Okay, so the question is giving us some information. It's told us, one, there's a population. It's also told us what the mean is. It's told us what the x value is that we're looking up. And it's even given us a z-score. The question that they're asking, though, is what is the standard deviation in this problem? So the way that we would write this out is, right, we'd fill in the different parts of the z-score formula. Just to remind you, the z-score formula for population would be z equals x minus mu over standard deviation, right? So I'm starting off with this -2 in the z spot because that's where they told us that z is -2. I'm also putting 59 in the x spot because they told us that x equals 59. The other bit of information that they gave us was what the mu was, right? They said mu was 65. So at this point now, my goal is to solve for our standard deviation. At this point, it's basically a simple algebra problem. We begin by first just taking care of what's going on with the subtraction problem. When we do that, we see that we got -2 equals -6 divided by the standard deviation. To solve this problem, the thing that I want to do is get that standard deviation on one side of the equal sign by itself. And the way I'm going to do it is I'm going to move it from where it is on the right side of the equation, of the equal sign, to the left side of the equal sign. The way I'm going to do that is by doing the exact operation that's going on presently, right? So right now, the standard deviation is part of a division problem. So to move it out of there, I'm going to multiply it out. When I do it on the right side of the equation, of the equal sign, cancels out on that side. I just need to also then put it in on the other side. So that when I go to write the equation now, it's going to look like this. -2 times that standard deviation equals -6. Remember that the goal here is to get that standard deviation by itself. So now I'm going to move that -2 out. The way I'm going to do it is right now it's part of a multiplication problem. So I'm going to divide it out, right? Doing that opposite operation. When I do that on this side, cancels out. So then I'm going to come over to this other side and now divide the -6 by the -2. Once I've done that, I see that I have a standard deviation of 3. So let's go ahead and look at our graph to see if that seems to be correct. First thing I want to do here is note that we've got our mu at 65. The question is asking about this x value of 59. And it's basically asking how many standard deviation units is that 59 away from the mean. So let's also think about that S row, right? So for S, we would have the 0 right there. And we may, before we did the math, we may not have known what the standard deviation was. So once we did the math, then we saw, oh, standard deviation is 3. So what we're going to do is we're going to say that we can put a standard deviation unit of 1 right here on the right side of the mean. But we're also going to put a standard deviation unit of 1 right here on the left side of the mean. How do I know that that standard deviation unit goes right there? I know it because I'm moving it away from the mean by 3. So then the question becomes, well, what x value would go above that standard deviation unit? Well, we're saying 65 minus the 3 equals 62, right? So that's where that 1, or the 1 would go right under the 62. So then the other question is, how many standard deviation units is that 59 away from the mean? Well, if we're moving away 3 units at a time, we've gone 3 here to 62. Now 3 here, 62 minus 3 gives us that 59. So we're saying, yeah, the 59 is 2 standard deviation units away from the mean. One other thing that we want to notice, though, is how that z equals -2 is working, right? So we could draw another row under the S row, and we could say that we have a z of 0 right under the mu. We have a z of 1 right under the standard deviation unit of 1. But the other thing that you want to see too is that going below the mean, right, numbers that are smaller than the mean, that's when we introduce our negative signs. So here, I wouldn't just write that I have a z unit of 1, I would say I have a z unit of -1. Same thing on this other side. I don't just say I have a z unit of 2, I have a z unit of -2 right there. And that's why we've got this -2 in our equation. Okay, so that's our first, or I think our second practice problem. I want to go ahead and move on now to a third practice problem. And that is this one here. So I'll start by reading it first. It says, in a population distribution, we have a score of x equals 54 that corresponds to a z of +2. And then we also have another score of 42 that's going to correspond to a z of -1. From there, the researchers are saying, what are the values for the mean and the standard deviation? Well, let's attempt to figure this out by first writing out the equation for this. What I'm saying is I've got two separate equations. I got an equation that's going to represent this x and that z value. And then there's going to be another equation that's going to represent this z and this x. And the way that they would look is like this. We'd say we've got this +2 that equals that 54, right? So going back to the way the equation looks, the z goes there, the x value goes there. Notice for this equation, though, we haven't been given any other information. We don't know what the mean is. We also don't know what the standard deviation is. We can say that's the same exact case with the other equation as well, right? So with the other equation, we were given this -1, and that was akin to this 42, but minus some unknown mean and some unknown standard deviation. So at this point, given all this information, I feel that I have not been given enough to answer the question, right? The question was, what are the values for the mean and the standard deviation, right? So what are the means in here and what are the standard deviations in here? I don't feel like I've been given enough information to figure it out mathematically. So now what I'm going to try and do is try and figure it out by plotting the different spots on a curve. And I'm just going to go ahead and put in whatever information I've got here to help me figure that out. First thing I guess I want to try and plot are the z-scores, right? Seems like those will be the easiest. I'll also note that I usually put those under the S, which also goes under the mean. I'm going to start with the z-scores because that's some information that I've been given, and I know where the z's go underneath the curve, right? I know that for the z row here, it's always going to have a 0 right under the mean. And I know that I'm going to have these z values that are going to go away from the mean in this way. I know I'm going to have, so I've got my first one, a +2. So we'll say our +2 is going to be right there. And then we also have this -1. And that -1 is going to go right there. Okay. So I've just plotted this bit of information, and I've plotted this bit of information. In each equation, we've got some other useful information as well. We've got these individual x values. And what each equation is saying is that we know this x value is above this 2, and we know this 42 is above this -1. How do we plot it on the graph? We say, okay, on the spot on the x-axis, where that +2 is, that's where we're going to say our 54 is. And on the spot where that -1 is on the x-axis, we're going to say that's where our 42 is. Okay, now from there, one thing that we can see is that we've got this bit of area between our first x value and our second x value. One thing that I'm curious about now is, well, how much space is in between this tick and this tick? The way I can figure that out is I can subtract the 42 from the 54, right? And that gives me 12. So what this 12 is saying is that there is 12 spaces between here and here. Now, as I start to think about, oh, okay, I got 12 ticks in that little range, I also know how many standard deviation units are present, right? We've got a standard deviation unit here, I've got a standard deviation unit there, and I've got a standard deviation unit there, right? So basically, I've got one standard deviation unit, a second standard deviation unit, and a third standard deviation unit. And those 3 standard deviation units take up 12 ticks. So now what I can say to myself, I know each one of these units is exactly the same size. So what I'm seeing now is a division problem. And that division problem is where I'm going to take that area that consists of 12 ticks, and I'm going to divide it by those 3 individual standard deviation units. When I do that, 12 divided by 3 gives me 4. So what that must mean then is that each standard deviation unit is 4 ticks big. Now that gives me information that I can use to plot these individual bits of data, right? So now I know what the let's put a 1 right there. Now I know what x value is 1 standard deviation unit away from the mean, and I from there can figure out what the mean is. How am I going to do it? I'm going to move 4 ticks at a time. I'm going to say, okay, here's an x value of 54. 1 standard deviation unit away from that is 50, right? Because I've moved 4 units away. Now, if I want to move another 4 units away, I can say 50 minus 4 is 46. So now, by plotting everything on the graph, I've just figured out what my mu is over here, and I've also figured out what my standard deviation is. I figured out that my mu is 46 and my standard deviation is 4. Okay, now that we've had some practice in calculating z-scores, I want to talk about the purpose. Why do we go about doing this? Why do we want to figure out what z's are corresponding to what x values? And that's going to be addressed in the next part of this lecture. Here where we're saying that what we want to do is use z-scores to standardize a distribution. What do I mean? I mean, we want to take a distribution of raw scores and take all of those raw scores and turn each raw score into a z-score. When we do that, this is how the transformation would occur. All of a sudden, our mean isn't going to be some x value, but instead now it's going to be some z value. And because we're saying that the mean z is always 0, we're going to start counting from 0. Okay, so what is it to transform raw scores into z-scores? First, that's the term that we use. We refer to this as transformation, or transforming the data. What do we do when we transform the data? We change x scores into z-scores. Why do we want to do this? Well, a big reason is so that we can compare distributions. Say, for instance, we have a distribution of data that some researcher collected. And maybe that distribution of data was the grades at the end of the semester from this class, right? So I'll have a bunch of scores for each student. And say I'd like to compare the scores that each student in this class got to the scores that students in another BC stats class got. You will not have done the same work as some other class. So the max score, right, the total number of points possible in the class is not going to be the same for you as it is for the students in another class. So we can't really compare them because they're two different totals. However, if we were to transform your scores and the other class's scores into z-scores, then they would be comparable, right? We compare your z's to the other class's z's. And now there can be this comparison that can occur. Okay, so with this, I just want to give an example of what this would look like. So let's say that we start off with some table of x values. Right, and that table of x values may include someone who got a 3, someone else who got a 4, and someone else who got a 2. We would start off evaluating this data in exactly the same way that we've been doing so far this semester. We'd get some sum of x, in this case it's 9. We'd get some n, in this case it's 3, right? And we'd use that information to then calculate some mean for the group. In this case, the mean also is 3. Now, in chapters 3 and 4, you may note that you've been getting all this data, so then you can go calculate sum of squares, right? That SS, or how do we say it? Sum of squares is the sum of the deviations squared, right? But why do we go get that? We get that so that we can get some sum of squares value, so then that we can turn that into some standard deviation value, right? Remember, sum of squares divided by basically your number of participants is going to give you your standard deviation. Okay, so let's say that we've gone and done that. We've gotten the standard deviation for this group. And the standard deviation, as it turns out, is 2. When we've done that, shoot, I just screwed up. I meant to use this other, okay, I'm going to do it this way. When we've done that, we've got all this information so that now we can add to our table, right? Our table began with the 3, 4, and the 2. Now what we can do is transform each of these scores into a corresponding z-score. How would we do that? Basically, we do 3 different z equations. Let's say, for that 3, for instance, we'd say z equals 3 minus 3 over 2. Let's do the z equation over again. So z is the score minus the mean divided by the standard deviation, right? So this 3 is that raw score, this 3 is the mean of the group, and that 2 is the standard deviation of the group. So it turns out that's going to give you 6 over 2, which will give you 3. I'm sorry. That's going to be 3 minus 3, so that's going to be 0 over 2. And 0 divided by 2 is 0. So on this set of data, the z-score that corresponds to an x value of 3 is 0. Same thing with calculating the z for 4. Right, here we go, z equals 4 minus 3 over 2 gives you 1 over 2, or 0.5. So we'd say the z value for 4 is 0.5. Same thing in calculating the z value for that 2. Here we'd say, okay, z equals 2 minus 3 over 2. What does that give you? Gives you negative 1 over 2, and that ends up giving you a negative 0.5, right? So the z value for 2 would be negative 0.5. Let's plot this just to make sure it fits, right? The way I'm going to do it, I'm going to say that we've got another curve here. We got our mean in the middle, and we're saying that we've got some mean value, right? And we know that that mean value is that 3, so we'll put 3 right there. Let's go ahead and just plot the z that's going to go with this. First, let's remember that when we plot z's, we're going to start with 0 being underneath the mean. And actually, as it turns out, that's why we've got a z of 0 for x value of 3, right? On our x-axis, where the 3 is, there's a 0 right below it. So let's think then, where would a 4? Well, actually, let's think of this. Where is the standard deviation units here? Let's say, remember, standard deviation unit starts out with 0 here. We go out 1 unit and 1 unit. What did we say standard deviation was? It's 2, right? So because our standard deviation is 2, if I were to say that a standard deviation unit of 1 on the x bar line, what number is it going to be right here? It's going to be 3 plus 2, which is, which is 5. And over here, what's going to be the x value above this standard deviation unit of 1? It's going to be 3 minus 2, which would be 1. Okay, so let's think then about this x value of 4 and why its z is 0.5. Well, we put the 4 there. The 4 goes right above your standard deviation value of 0.5, but also your z value of 0.5. Right? So that's why we have a 4 that has 0.5 as a z. But then think about this 2. Why does this 2 have a negative 0.5? Well, the 2 is right there. It's smack in the middle of 0 and 1. So, we're going to put a 0.5 right there. But remember, because we're below the mean, that 0.5 is a negative 0.5. And so that's why we have a negative 0.5 here. Okay, so that's our example of what happens when we take our x values and we transform all of them into z values. You see how the table changes, but then you also see how the graph changes as well. Okay, from here, I now want to just end by talking about 3 properties that you're always going to find when you transform x values into z's. First thing that you're always going to find is that the z-score distribution curve is the same as the original, right? So for instance, look at these 2 curves. This was the curve for the raw scores, the x's, And then this is the curve after those raw scores got turned into z-values. The thing that we're saying here is z-score distribution curve is the same as the original. The shape of the curve does not change from its original form. That's what this first point is saying. The second point, z-distribution mean will always be 0. What do we mean with that? Right, so we take the mean that used to be some x value, we transform all the data, and now all of a sudden the mean is always 0. Notice it was 0 here, and it also was 0 here. Okay, so we've got that explained. And now the third point is the z-distribution standard deviation will always be 1. Okay, so with that we're saying standard deviation over here could have been any number. It was just the distance from the mean. But now when we transform the data, the distance from the mean in terms of standard deviation units is always going to be 1 tick away from the mean. I think I'm showing you that here as well. Right, so here was where we had raw scores or x scores, and here's now where we have z's. Let's see. It's not showing the thing for the first part, the curve. Well, actually it is, right? Here looks like we have a kind of like a skewed curve. Same thing over here, the curve is still skewed. For the second point, the z-distribution mean will always be 0, right? So it started off being some average of the x values. Now it's always going to be 0. Same thing here, the z-distribution standard deviation will always be 1. Before, it could have been any number of units. Now it's always going to be 1 unit. Okay, so that's everything I've got for Chapter 5. Thank you very much, and I'll see you in the odds problems.